Thank you. Okay, the micro is fine, working, everything good. So I just want to show my triple affiliation. So I have my permanent position in Main Astronomical Observatory in Ukraine, but I oftenly show up in NAOC, in Chinese Academy of Sciences, and also in RE in Heidelberg. So the points which I want to concentrate in this 20 minutes, which left for me. So basically, first few slides I show a collaboration and some very, very quick introduction about what is direct N-body and what is the difference and how I just feel to say, I feel myself to say something about what exists, you know, N-body also not only in a gadget or Picardie graph. So after I would concentrate on the hardware which we use and our codes, and after, if I have enough time, hopefully, I show some astrophysical test results. First of all, our binary black hole evolution and galaxy merger simulations, and also some attempt where we use the SPH and 3 GPU codes and the results. So first about the collaboration, I think the best if you just go to the Silk Road BAO ACCN webpage, and you can look all the personal stuff. I don't want to say to all of them, but just I want to mention Rainer Spursem, who is our basically leading scientist in a group, and he is basically the person where we all working around, and he is our basically main person in the group. So about the collaboration and some grants which we are funded in the last years. So first of all, it's the Silk Road project grant in the Chinese Academy of Sciences, which allowed to build a big computer, big GPU computer. Yesterday it was a remark, but do we have any dedicated astrophysical GPU computer? And I want to say yes, we have some dedicated GPU computers for astrophysics, and which is working in a supercomputer mode. And a nice example is a Milky Way system, is in which was built in a DFG on the base of a DFG money under the SFB 881, and it is actually operated in one of the biggest supercomputer center in Germany, in Jülich. So this is one of the part of SFB. So also I want to mention the some collaboration which we founded in International Center of Computer Science between Berkeley, Beijing, and Heidelberg. And also I want to draw your attention about this website. Please just visit it and look into this astrophysical multiscale environment. And if you look on it, you can find that basically we try to do some code development where we can include everything which we are talking now, not only gravitational dynamics, but hydrodynamics, radiative transfer, even stellar evolution. So a few words about the direct N-body simulation. So I want to mention the name of Sverre Arset, who was a pioneering guy in this business. He started around mid-60s, and he constantly developed his codes, starting from N-body 1 up to now to N-body 6, and the plus is an MPI version of N-body 6. And here it has some acronyms. So this is a Hermit individual time-step scheme. This is a KS regularization for the binaries, which you probably in a cosmological simulation don't have because of resolution, and you are lucky.
Not yet.
Not yet, but when you move to 10 parsec, probably you can get some binaries, so unavoidably. And you're facing a problem of regularization. And so the latest N-body 5 and N-body 6 codes, and also N-body 6++ is using the so-called Ahmed Cohen neighbor scheme. So it's not fully anymore direct N-body because you're not calculating every time step the full forces from all the particles, but only calculated the neighbor forces, and you split your force basically to regular and irregular force. So anyway, I just left you with these links, and you can look on it and learn a little bit. So about the code development and which code we are using right now, and what's what I want to present. So Thomas was in this 2011 IST meeting, and I was also, and the reason why I was, we're getting an award of P-Race community for this astrophysical particle simulation with large custom GPU clusters on 3 continents. And you see the whole bunch of people. We was both of us, this is myself, and this is Guillermo Marcus. He worked at this time in Mannheim University. And this is where we get an award. It was very nice. It was very good. So, about the GPU hardware, I just putting this slide because I like the latest Titan card. I just a couple of weeks ago get one and putting in my workstation, and I'm very happy. If NVIDIA people is here already, I can just congratulate him. Yeah, it looks very nice. Especially I like the lights, you know, which is working on it and say Titan, you know. This is cool. So, so about the business. So we start really to use the GPU from 2007. So roughly around middle of 2007, we managed to port one of our legacy code, the grape code, to the GPU. And basically in the last 6 years, we're constantly using a different GPUs, different architectures, different CUDAs. So, but I just want to make one note here. But if in 2007, 2008, we roughly have 128 cores on the GPU card, nowadays in this Titan card we have almost 2,700. It's have some kind of small cheating in a sense that the frequency is not the same nowadays as it was. But in principle, if you look, you're getting a factor of 10 or even 20 speed up, and this is what we really have in the GPU business. In 5 years, I think is a quite impressive speed up. So about the top 500, so the prognosis was around 2018, we're getting this exaflop system, if everything going fine, and I think it's unavoidably the system should have some accelerators, whatever it will be, NVIDIA GPU or whatever accelerator, but I think without accelerator it's just impossible to have this performance. This slide I borrow from Berkeley, and the point why I show it, just to point your attention for a huge gap which we sometimes have between a custom code or a real application and this Limpak performance, which always show it in this top 500. So this is the orders, yeah. So it's mean at least 1 order, 2 order, always this gap, and in our direct summation codes we try to eliminate this gap or make it become as much as small possible. So some old picture of myself. Yeah. So this is around 2005, yeah, when we still have an old cluster, and in 2008 we already built a new GPU cluster in Heidelberg University. This is in Kiev in Ukraine. We have a smaller 16-node GPU cluster, and this is in Beijing in NAOC. I have no more clusters, guys, so it's all. No more photos of me. So this is an 85-node cluster which we built in beginning of 2010. So actually it was in November 2009, but really start to functionally in 2010. So this is some internal information. So we have in total 170 Tesla. This is an older cards. Right now we are changing to Kepler K20. I'm very happy that we have a very good interconnection between the nodes. So this is a 20 gigabyte per second DDR InfiniBand network, which has helped us a lot to work. Oh, I'm wrong. So I have one more slide. This is a Milky Way cluster, which I mentioned already. This is a specially dedicated supercomputer only for astrophysics, nothing else. And this is operated under the SFB 881. And actually the name of this SFB 881, the Milky Way system, or evolution of a Milky Way system. And the cluster name is also Milky Way. And this is Rainer Spusa. So, so here we have roughly 200 nodes with whatever, I think in each node we have 2 GPU cards, so in total we have 408 GPU cards. So this is how it looks like. This is some smallest cluster in same in RE environment. This is our newest one, which is a small one, only 12 node, but we already use the K20 and get a good performance. This is our biggest system, which we use. This is in the Institute of Process Engineering in Beijing, in a Chinese Academy of Sciences. This cluster is famous because it was one of the first one, if not the first one, which using Tesla C2050 cards. in a massive way. So we have here roughly 2,200 GPUs. And our biggest performance run we did on this cluster. Each node have 6 cards. Right? So I think I just need to speed up a little bit. So about the idea of this n-body code. So in a direct summation, we usually just make the all-to-all summation of the gravitational forces between all the particles. This is how we did it in older time. Somebody who still, probably everybody still recognize the fortran. So this is how we do it nowadays. This is a CUDA, which is not much difference compared to the C, basically. The tricks, of course, is behind. And the tricks is what we try to use the hierarchical individual block time step. So we don't calculate all the forces between all the particles each time. We just calculate the fractional forces between the active particles and all the particles. So how we do it in a parallel way, of course, we distribute the job between the nodes. Actually, the codes is available publicly in FTP site. This is the code which acronym has PHI. It means parallel Hermite integration on GRAPE, which was originally developed for the GRAPE. And we have now the same parallel Hermite integration on GPU. So, so basically, this is what I said. The job is basically divided between nodes, divided between the GPU or GRAPE cards, and in each node you calculate the fractional forces between the active particles and the rest of the particles in a memory. And after you need some communication scheme to get the full forces which is acting from all the particle to the active particles. So in all time we do this hardware acceleration using the GRAPE. Nowadays we're using all the possible ways. So the GPU is actually only one. We're extensively using also the AVX and the ECC, SSE instructions. The AVX performs very good. I was really surprised when roughly one and a half year ago I tried the AVX and I get a very good performance. So the test results, so this is the usually test which we're using in n-body community. This is a Plummer sphere which we just generate some mass distribution, or this is density distribution actually. And this is with our funny normalization, so where the gravitational constant, the mass, is equal to 1 and the total energy is equal to -1/4. This is come back to something like old 70s when these fathers of this n-body codes decide to have some kind of normalization, and we still use it. So basically how it looks like the system after some time step, I just quickly plot, I think this is up to 26 n-body time units. So you see what basically in the center we start to form. This is a cumulative particle distribution, a cumulative mass distribution. I think it's particle distribution. And this is how it looks like the time step hierarchy. So this is one of the point which I want to mention. So we usually have here large order of differences between the particle time step. Yeah. So we did our big performance run. Yeah, we did our performance run on this IPE cluster, and where is the code is, where is the paper, and we tested all the parts of the code, divided in very carefully. I don't go through all, but we have basically, so we have all the part which is connected to the host, the GPU, the communication between a host and the GPU, the MPI communication between the nodes. But in the end, we figure out that basically the most important part is the two parts, is the MPI and the GPU force calculation. So just based on this, you can already make some model. So when we have our experimental data, and this is basically our experimental data. So for different processor numbers, for different particle numbers, we just make a run and make one n-body time unit integration. And you see what basically for largest particle number, something like, okay, for here is 4 million. On 85 node, we need roughly more than 1 day to finish one n-body time unit. So this is some pie chart, which type of parts we have. So this is an efficiency which is shown what basically for small particle number, of course, the efficiency immediately degrades when you go for large numbers. And this is one point which I also want to mention, and I didn't see in a previous presentation. So the scalings I see, somebody showed already the scalings, but I think nobody shows the performance. So really, what is a teraflops, what is a petaflops, or whatever you reach using your code. And in Exascale conference, I think it's a little bit strange to not talking about the real performance, because this is actually show you how effectively you can use your hardware. So we know what the NVIDIA guys is always claim that, okay, our GPU give us whatever hundreds of gigaflops or whatever thousands of gigaflops nowadays. But the other point is what really use your code. And for, I think it was an Alauhu cluster for this 1060 GPU, we're getting almost 330 gigaflops speed. Yeah, so this is basically when you plot the speed. So this is an ideal scaling and the ideal speed for large particle number. So this is one point which I want to also mention. So this is unavoidably of any parallel code, whatever you do, whatever is your domain decomposition or whatever you force calculation routine you use, in some point you hit the problem what you have to deal with a communication between the nodes. And in our cases, this is basically what is limited. So you have two parts in your formula or in your performance curve or in timings. One, this is proportional roughly to the number of nodes. This is a communication between the nodes. And one which is proportional 1 over the nodes. This is basically the calculation part if everything done well and you have a perfect code which written in the best professionals. But anyway, at some point, these two curves is match and you coming to this shallow part and after even become worse the situation. So, of course, in our codes we also have this, but this is the largest simulation which we really manage, and we see what for 6 million particle, we did the simulation actually in 1,536 GPU card. Each card have 448 nodes, so in roughly we reach the 700,000 core in this simulation, and we're getting a very good performance. It was around 360 teraflops on the system. About the fault tolerance. So you remember I said what this IPE cluster have 2,200 GPU cards. And why I don't have here the 2,000 points? Because at the moment when we spent for this testing 3 days, it was just impossible to manage to have all the 2,000, thank you, all the 2,000 GPU cards working. So a maximum number which I can have, it's roughly this 1,500. So, and whatever we did using all the system administrators and whatever, it's never worked. We never have a full cluster. Okay, I think I just want to spend a little bit more time on this one plot and after just jump to the conclusion. So this is actually our points. This dotted lines is a prognosis. So just using our performance formula, we can actually calculate what we have if we have 2,000 or 4,000 or 7,000 cores. This plot was actually did to submit to application to TNH1A and the TNH1 to the supercomputer and just show which performance. So we promised to get something like 1 petaflops if we manage to have the 7,000 core, 7,000 GPUs, and we can use the speed of a LAN, the network, which is roughly 4 times compared to what we have. So, last slide, good. Or almost. No, so, last slide. so this is our real data point. And here I just did the exercise. So I asked myself, okay, what's happened if we have a 4 times faster LAN between the nodes? And instead of this curve for 6 million particle, I'm getting this. Yeah? So I'm getting more than 1 petaflops if I can manage to have 16,000 GPU. But if I keep the same network and I just have 10 times faster GPU, actually this is not help too much. So I'm getting this curve, which in the beginning roughly 10 times larger, but after it's saturated, and come to a fixed position. So, my conclusion. So if we want to move really the exaflops, which is here, with our whatever final or new Phi GPU code, we need to have not only the fast LAN, fast network, but we also need to have a fast cards, and both. And even in this case, even if we scale it up, our application, to have instead of 6 million, have something like 300 million particles, which is our goal to modeling the bulge of a galaxy star by star, even in this case, we probably get only a few hundred petaflops and not the exaflop. Okay, so now I need to quickly show all the 60 slides and go to my conclusion. No. You don't need to remember this. Yeah, you can have a question. Yes. You can have a question.